Hello everyone. Okay, continue our discussion on governors. I discussed quota governor and I want to move on that. And before I go to the next type of governor which we are supposed to discuss as per syllabus, that is Hartnell Governor. Okay, before I do that, okay, I have a small classification which you have already gone through. So you all know governor. Governor is the one which is an attachment which controls or which maintains a constant speed for the engine. Okay, if the engine load changes, then only the speed of the engine will change. But we don't want that change, and we want to have to run the engine at a constant speed irrespective of the load on the engine, and therefore the governor is needed. So governor, why governor is required? Because to have the maximum efficiency, to get the maximum, extract maximum efficiency from the engine, we need a governor. So there are basically two types of governors, centrifugal governor and inertia governor. Okay. Centrifugal governor works on the basis of the change in the centrifugal force. As you all know, centrifugal force is equal to m into omega square into r. When omega changes, centrifugal force changes, and therefore the change in speed, okay, d omega is responsible for the change in the centrifugal force, and therefore centrifugal force works on the change in the speed, d omega. So depending, this is going to function what is called as d omega. If d omega is changing, if there is a value for d omega, then this governor changes. The centrifugal force changes, the sleeve position changes, and that is how it works. The inertia governor, okay, so this works on the change in the inertia force. That is nothing but the change in the acceleration. So inertia torque, that is d by dt of d omega upon dt. d omega upon dt is nothing but the acceleration. This is nothing but the change in the acceleration. That is, I shall take it. D of d omega by dt. This is nothing but the change in the acceleration. The change in the acceleration is responsible for the functioning of inertia governor. The change in the speed is responsible for the functioning of centrifugal governor. So, looking at this, it appears to be better. So, the rate of change of speed, okay, is going to be taken into account in inertia governor, and this appears to be more efficient. This governor appears to be more efficient looking at this, the way in which it works. But still these governors are not popular because it is not that easy to construct this inertia governor, or other way, it is very easy to construct these centrifugal governors and it is not easy to construct inertia governor. Because of this reason, we have what is called as this branch is more popular and more common, more realistic, and therefore we concentrate only on centrifugal governor. Okay, centrifugal governor itself, then again it is further classified into two categories, what is called as unloaded governor and loaded governor. So as you all know that centrifugal governor, every centrifugal governor has what is called as sleeve. Sleeve is a must for centrifugal governor, and the position of the sleeve is going to decide what is the speed of the engine or the speed of the governor spindle. So whenever there is change in the speed, the sleeve will change its position, and the change in the sleeve position is responsible for the adjusting the supply valve to the engine, and therefore the sleeve displacement is very crucial. If you have very little, very small sleeve displacement, then that may not be sufficient to alter the supply valve, and in that case the governor may not work, though there is change in the speed and there is change in the sleeve position which is very small. For a very effective functioning of the governor, the sleeve displacement, if it is made more larger displacement, then the governor will function a better one. Okay, so this unloaded governor, so unloaded and loaded governor. The meaning of this is loaded. Load means force. So here the force, depending on the force on the sleeve, we call it as the if you have a force on the sleeve, then we call it as loaded governor. If you don't have any force on the sleeve, then we call it as unloaded governor. Okay, in unloaded governor, and we have a type which is called as VAT governor, and the sleeve is, there is no force on the sleeve. So even the weight of the sleeve is also a force, and therefore in VAT governor, the sleeve is of negligible mass. Therefore, there is no force on the sleeve. Therefore, with respect to the porter governor, if I say that if you make ms equal to 0, then we have what is called as VAT governor. ms, the mass of the sleeve is 0, that governor is called as a VAT governor, and that is why we call it as unloaded governor. So then if we are able to have force on the sleeve, so how we can have it? By different ways. So I can make the sleeve itself very heavy. That weight itself is the force on the sleeve. That is how I can have loaded governor. That is what we have in the porter governor. Or if the sleeve is very light, then I can place some dead weight, extra dead weight on the sleeve, and that is how I can have some force on the sleeve, and that is how I can call it as loaded governor. By chance, if your sleeve of the centrifugal governor is very heavy, or I have some extra weight on that sleeve, then that type of loaded governor is what is called as dead weight type of centrifugal governor. Dead weight type of loaded centrifugal governor. And there are couple of types of these types of governors. That is porter governor is one, the other one is coil. Okay, and porter is the one which we have studied in our discussion. As per syllabus, we have discussed porter governor and we have understood that. And before I proceed with the other type, let me complete this and then come back. Why loaded governor? What is the use of that? Okay, there is another way of having load on the sleeve. So you all are familiar with the spring, say helical spring. Okay, helical spring, if I apply a compressive force, compress it, or if I pull it and to increase the length of the spring, then I need to apply force. And the force, whatever I pull, depending upon that, I have what is the extension or I have compression of the spring. So the load on the sleeve depends upon what is the compression of the spring or what is the extension of the spring. So therefore the load is not constant. In case of dead weight type, the load on the sleeve is constant whether the sleeve is in its bottommost position or whether the sleeve is at its topmost position or anywhere. The load is constant. But in case of spring loaded governor, the load on the spring on the sleeve is not constant, it is varying. So it is a variable type of loaded governor. The load on the sleeve is varying. And how it is going to be achieved, that we are going to study. So one of the type of, say, number of spring loaded governors are there, depending upon the construction. There are so many types. And as per syllabus, we are supposed to study what is called as Hartnell governor. Okay, but why do we need loaded governor? Okay, before I go to the Hartnell governor, I just want to impress upon you what is the importance of this. Why these governors are not common? So why we have only loaded governors? I just want to impress upon you. So go back, as I said. So the position of the sleeve is very important, and the position of the sleeve is constant as long as the engine speed is constant. If the engine load changes, the speed changes, and the governor's sleeve position also changes. The sleeve movement, so whenever there is change in the position of the sleeve, okay, from one position to another position, I call it as sleeve displacement. Sleeve displacement is very, very important. If you have a larger sleeve displacement, then there will be more effective adjustment in the supply valve, and the purpose of maintaining the constant speed may happen very easily. But if the sleeve displacement is very, very, very small, in that case it becomes difficult to maintain the constant speed. So in the case of unloaded governor, we have that very, very small sleeve displacement, and therefore it is difficult to maintain the constant speed, and hence we don't find VAT governor. But in case of loaded governor, the sleeve displacement is made heavy for a small change in speed, and therefore we find only this dead weight type or spring loaded type or in general the loaded governors. So therefore you have understood the importance of loaded governor, and loaded governors are of two types, this dead weight type and spring loaded. So among this we have studied only one type, rotor type, and now spring loaded governor we shall take up what is called as Hartnell governor. So Hartnell governor, this is what we will see now. So Hartnell governor, so we shall see the construction of the Hartnell governor. Before that, I would like to spend a few minutes on springs. The element spring is a very common, you have seen it. Okay, I don't want to go in detail what is the advantage of spring, why springs are required, what are the functions of the spring, etc. What are the types of spring, all that I am not going through. We all are very common. Say for example, you have something like this. Okay. Something like this. Okay. So I shall call this, I hope this looks like spring. So this spring is called as a helical spring, whatever what I have shown. Helical spring. Okay, in automobiles, in trucks, cars, okay, suspension. So there also you find spring, and that spring is called as a leaf spring. Okay, now as you come back here, you have coils, you have small wire. The wire is wound in the form of coils. You have a number of coils, and there is a distance between the two coils. Okay, and depending upon this distance, okay, whether it is small or whether it is large, you classify these springs into what is called as either tension spring or compression spring. Say tension spring or compression spring. This also is based on the kind of load the spring is subjected to. Okay, if this end is fixed and you apply this kind of load, so we have tensile load and the spring is called as tension. And if you apply compressive load like this, then the spring is called as compression spring. Okay, so you can easily, it is not that even in there is a small change in the construction of this tension spring and compression spring also. Okay, if in case of tension springs, the distance between the two coils is very small. They almost, the coils touch each other, and when you apply the force, tensile force, the coils, distance between the two coils will increase. That is how the displacement of the spring will take place. If the distance between the two coils is quite large, more, in that case the spring is called as compression spring, and when you apply compressive load, the coils come closer to each other and the amount of compression total, okay, that depends upon what is the force. So now in case of Hartnell spring, so we are going to have what is called as the compression spring. Okay, I have a spring of this type. Okay, these are the number of coils, and in your design of machine elements, either one or two, you are going to study a topic what is called as a spring design, and there, so what is the distance between the two coils, number of coils, etc., you are going to study. But whatever little required for my study, okay, for Hartnell's governor, I shall explain it. Okay, I have taken a helical spring which is compression type, and I have kept it on the surface of a table, say on ground. Okay, this is ground, I have kept it, and I have not applied any load. I just measure what is the length of the spring along the axis. Along the axis, when there is no load, okay, I just measure it. And if you keep it vertical, you may call it as height also. You may keep it in the horizontal, then we call it as length. Okay, whether it's length of the spring or height of the spring, both of them are one and the same. And right now there is no load. This length is called as the free length. We call it as free length of the spring. Right now there is no load acting on it. Okay, now suppose I apply whatever load. So I apply certain load, so F is the load I apply. The moment I apply load, okay, I know that the coils, all the coils come closer and closer, and whatever this level now, and let me assume that it comes somewhere here. Now the spring has become only from here to here. The spring, okay, has been compressed up here, and this is now the load. And now also again I measure what is called as L. L is the length of the compressed spring which is under the action of F. If the force is different, then L also will be different because the compression, the amount of compression will be different. Then L free minus L, this will give you what is the compression of the spring. Okay, delta L. Then to have this compression, how much force? To have compression delta L, I require a force F. And how much force is required to have unit compression? If I want to have unit compression, then how much force is required? And that is what is called as stiffness of the spring, which is normally denoted by K. K is the stiffness of the spring, and this is defined by F divided by delta L. So delta L is the compression, amount of compression, and K is the stiffness and the force. To get delta L, F is required, and the force required for unit deflection, unit compression is called as the stiffness of the spring, and it is having the unit of Newton. F is in Newton and delta L is in meters. Then Newton per meter, Newton per millimeter, Newton per centimeter. This is a very common unit for K. And K happens to be a linear one. K happens to be a linear one. And therefore, okay, and if I have some other deflection, say if I have a deflection of delta L1, say, I don't have deflection delta L, I have a deflection delta L1, then how much force I require? Okay, I can easily calculate delta L1 multiplied by K is equal to F1. So, if you know K, then you can easily find out how much force has been applied to get a certain compression delta L1, and this is very, very important. So, therefore, if I can say K is equal to F divided by delta L, or this is equal to F1 divided by delta L1, this is also equal to F2 divided by delta L2, etc. Okay, so one small understanding now. Small, so what we have understood or not, just to check that. So I have a small question. Okay, a spring already. Okay, we can take the same spring, and now I have applied what is called as F1. Okay, I have applied a force F1 already. A force has been applied, and now let me say that I have a length L1. So L free is the free length. I have applied force F1 and I have got L1. Okay, and I have found out and I know what is the value of K of this. K for this spring is also known. This also is known to me. Okay, so now I have further compressed the spring, and now this length is L2. So how much extra force is required to have this? Or in other words, okay, so how much force F2 is required here? Then F2 minus F1 will tell you how much extra force is required. Okay, that can be easily obtained. So what is that? F1 divided by delta L1 is also equal to F2 divided by delta L2. Okay, F1 divided by delta L2. So what is delta L1? F1 divided by delta L1 is nothing but length, free length minus L1. This is also equal to F2 divided by L free minus L2. So from this you can easily find out what is F2. So knowing F1, this is known and this also is known, and therefore you can easily find out what is F2. And so once you know F2, you can find out F2 minus F1, and that is how you can find out how much extra force is required. So this is going to be very useful for us, okay, later on, and probably, so when it is required during the discussion of Hartnell Governor, I shall again explain you what is the meaning of this, probably with values that time. Okay, now I shall go to the construction of a Hartnell Governor, how Hartnell Governor looks like. So Hartnell Governor is also a centrifugal governor. It is also a centrifugal governor. Okay. Okay, I shall draw the spindle of the Hartnell Governor. Okay, you have something like this. You have basically a stepped shaft, and a similar thing you have it in case of a porter governor also. Probably I need to show it. I represented the spindle of the porter governor just by a line. Okay, so you have a stepped shaft. Probably this is all threaded. And probably this portion also is threaded. Okay, this is so why a stepped shaft? Basically to support the skeleton whatever I introduce. Similarly, in case of porter governor, the upper collar which was we were telling that it is fixed. Okay, similarly here also you have the upper end of the skeleton must be fixed. Okay, now I have what is called as call it a skeleton of the porter governor, and you have something like this. The diagram, this is supposed to be symmetric. Okay, whatever this arm like thing, no? So there is a hole here, and that has been introduced, and the hole is of this size only, and therefore this can come up to here only, further cannot come down. And probably you insert some nuts here, and probably you may have one more nut, what we call it as a lock nut, so that it doesn't come out. Okay, this is how. Okay, now then what we have is so to this skeleton. And here at the bottom end, we have what are called as a bell crank levers, bell crank lever. Okay, this is something like this. It is a single piece. Okay, the angle between this arm and this arm right now is 90 degrees, and it may be different also. So this is called as what is called as bell crank lever. Okay, at the two ends, wherever you do this. Okay, this is the hinge point of a bell crank lever, and that instead of showing the arm like this, I shall show it now as if it is a line like thing. Please remember, but it is not really like that. It is having some dimensions which I am not showing. Okay, there is a hinge point here. Similarly here, what I have is similar thing. Okay, so similarly this side also. And here also, they are identical. This length and this length, they are same. Okay. This is the bell crank lever which has been hinged here, and here we have what called as governor ball. The governor ball is here, and this here you have a small roller. You have a roller. And this roller is going to support what is called as sleeve. You have a sleeve. This is the sleeve. This sleeve can go up and down. Okay, the roller is touching here, and here you have what is called as a spring is there. The spring is placed on the sleeve, and there will be one nut. Okay, so as I have shown you, this spindle also threaded. Okay, the purpose is you have a nut like thing which can move, and using this nut, even in the sleeve in the lowest position, wherever it is, that time also you can compress, and you can compress the spring and see that even when the sleeve is at its lowest position, that time also you have some force on the sleeve. And if you don't want any such force, you can loosen it and make it the free leg, and that time you will not have any force when the sleeve is in its bottommost position. So please here, and this is how the construction. Okay, of course, this is governor spindle is connected to the spindle of the shaft of the motor, and maybe whatever the drive it may be. And when the load on the engine is constant, this also is constant. The speed of this also is constant. If the speed changes, and this speed also changes. So when the speed of this changes, these valves which are revolving, so this spindle and this portion also is revolving, and the speed of this also will change. If the speed increases, these governor valves will go out, and they lift the sleeve. And when they lift the sleeve is further compressed. Please remember, the load on the sleeve is different. If the speed goes down, in that case the valves move inwards. When the valves move inwards, the sleeve will go down. There is expansion of the spring, and therefore the load due to the spring on the sleeve is going to decrease, and that is how the load on the sleeve is going to change continuously depending upon what is the compression of the spring. Okay, so this is how the Hartnell governor looks like, and the analysis of this we shall see it in our next class. Okay, thank you.